Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we will continue with the uniformity aspects of Drawframe sliver. Okay. Now we will discuss the spectrogram. So, a spectrogram is special diagram, special actually the diagram where we get the this is the form where we get the wavelength of periodic fault. So, spectrogram can only identify the periodic fault. Okay. So, and if there is non-periodic fault, random fault, so spectrogram will not be able to identify. So, and there will be a peak which can be observed where the wavelength is there. So, at particular wavelength, so wavelength is given in the x axis and y axis it is a amplitude. So, I will discuss all these issues in this section. So, amplitude of periodic mass variation is plotted against the wavelength. So, here in any wave we have seen earlier, any wave, this is the wave. So, the maximum variation is actually termed as amplitude, but here the term amplitude in the spectrogram is actually different. So, this is not the maximum variation. So, amplitude is a measure of the number of times the fault of that repeat length occurs, not the extent of irregularity, that we must understand clearly. Now, let me draw two fibrous assembly, two sliver suppose. Okay. One sliver is having say a random variation. So, these are the random variation of that sliver. So, another sliver we can have suppose perfectly even, almost there is no variation, and third sliver which is having periodic variation. So, this is a periodic variation. Now, sliver A, B, C. So, sliver A and B, for that spectrogram will not be useful, but when there is only periodic fault, then the spectrogram will be there, and the spectrogram of a random variation and spectrogram of a perfectly even sliver. So, they will look almost same. So, spectrogram will not be able to identify the difference, but when there is there is periodic variation, in that case the spectrogram will come into picture. Now, this is one variation here, this is the wavelength, okay, wavelength, and another material, another sliver where wavelength is small. So, this is the wavelength of that material. Now, here in spectrogram, this is the spectrogram, in x axis the the wavelength, and in y axis it is the amplitude. Amplitude is given in the y axis. Now, amplitude is a measure of number of times the fault, that repeat of that repeat length. Now, here the repeat length, suppose it is a 100 meter, number of repeat. So, this is the basic spectrogram, the shape of the basic spectrogram is like this. So, number of repeat here 100 meter, suppose the wavelength here say 1 meter, 1 meter wavelength. So, there will be 100 times these things will be repeated, this waves will be repeated, okay. That fault will be repeated 100 times. So, what we are discussing, so let us see two slivers. One is with variation wavelength, longer wavelength. Suppose we have tested 100 meter sliver, this wavelength is say, suppose this is the wavelength, maybe say 10 meter wavelength. In another sliver we have tested with a smaller, shorter wavelength. Okay. This is A and sliver B, shorter wavelength is say 1 meter. So, here in the spectrogram what it will do, it measures the number of times the fault repeats. So, of that length. So, if it is 1 meter, so x axis is the length and y axis is the amplitude. So, here if it is 1 meter and the x axis is in logarithmic scale. So, here say 10 meter, like in that way. So, 1 meter, in 1 meter we will find the number of repeat will be say 100, 100 times the fault will repeat. So, y axis there will be 100, that is histogram will be drawn, so 100 times that will be there. So, this is the basic spectrogram here, and here the spectrogram will be up 10 times. So, that is the amplitude. So, amplitude is the number of times the fault repeats, okay, of that particular length. From the speed at which the yarn is running through the capacitance type sensor that we have discussed earlier, the frequencies are converted into wavelength, that if we know the speed, from there we can get the wavelength and plotted in finite number of discrete wavelength in steps. So, that will give us the spectrogram. This histograms are then plotted automatically, and this height of the histogram is the amplitude. It helps in locating the fault, and at the point it is, and where the fault is generated due to the roller defect particularly, and where it is periodic in nature. The spreading of hump are due to periodic fault, but it is a due to drafting wave. I will show you. This is the spectrogram as we know. If it is due to the roller defect, there will be perfect chimney or hump, perfect chimney will be there, perfect location it will be there. Okay. That we can get, but if it is due to drafting wave, so there will be series of humps. So, this is actually the spreading of humps will be there, that will show that there is a problem of drafting wave. Okay. The wavelength of drafting wave is 2.5 to 3 inch for cotton. Now, this is the spectrogram, and here we can see this is 1 meter, and in that x axis actually is a cut length, or it is a basically यहाँ पे that is and y axis it is a amplitude. So, cut length means here we are talking about the wavelength. The numerical value of u percent and c percent are not influenced by the periodic variation. So, the spectrogram will not be able to identify the numerical value or segregate the two product with higher u percent or lower u percent. It can only identify the periodic fault. The spectrogram is a graphical representation of specially designed for identifying and analysis of periodic fault. Now, you can see the x axis represents wavelength, and it is in typically it is in the logarithmic scale, y axis represent the amplitude of the fault. Now, significance zone we can identify. So, there will in a spectrogram we may find, this is a typical spectrogram. So, we may find different humps, okay, of different size. So, are all these humps significant? So, do we target the PA length, the wavelength for all the humps? It is not that. So, depending on the height of the amplitude, height or chimney height, we can take action. And this is the 3D spectrogram, where we want to compare a number of specimen at a time. Now, spectrogram of a fault free yarn stand, this is the basic spectrogram, and this will be the almost same for a yarn without any periodic fault. So, we will get the spectrogram like this, same spectrogram, and spectrogram with pronounced fault, periodic fault. The faults show up in the spectrograms in two ways, chimney type and hill type. And chimney type, this is the chimney type, where this chimney type is mainly due to the either some fault in the gear or the eccentricity of roller. So, that we will get chimney type where clear peak is observed. But in case of problem in the drafting zone, suppose the fiber length it is there is a large number of floating fibers, drafting wave generates, there we get the hill type spectrogram, and that both this hill type and chimney type they are useful. So, depending on their nature we can take action. Chimney is due to mechanical fault of the machinery, and hill type is due to drafting wave. So, chimney type spectrogram, this we have seen here. Not all faults result the deterioration of the fabric quality. So, the extent of the influence of a periodic mass variation on the fabric quality is not only dependent on the amplitude of the spectrogram peak, but also with the on the width and type of the woven fabric. So, that we can get special effect. So, if we see there is a spectrogram or there is a periodic wave, if the width matches there with that fabric, so that we will get some special defect which is not acceptable. So, you can see here, based on controlled trials as well as experience on real industrial situation, the following general rules are adopted. So, what are the general rules? So, P is the height of the chimney above the basic spectrogram, and B is the height at that point where chimney is occurring, and the relationship is the P should be more than equal to half of B 2. If it is there, then the fault is considered to be significantly serious and warning can be given, and if it is less than that, then we do not need to give, we can just take some precaution, but we do not have to be worried about the correction. Now, here we can see it does not depend on the height, actual height of the P, absolute value of P is not that important. The basically the relationship between the base of that side, that means here at position A and position B. In position A, the height of the spectrogram, that chimney will be definitely high, because here the wavelength is low. So, for a certain length, the repeat number of repeat will be very high here. So, here similarly it will be low, but the thing is that as compared to B. So, what is the size of P? So, this B is also very significant here. At B point it is also very significant. Now, how the doubling effect in the draw frame influence the spectrogram? Now, the condition is that most of the mass variation in the strand of staple fiber is sinusoidal in nature. So, it is basically this will be sinusoidal in nature. Hence, every thick place is followed by a thin place and vice versa, that we have seen when we discuss the drafting wave, and also during the discussion of the roller eccentricity, there will be some portion, there will be stretch, high draft followed by low draft. So, that will create the sinusoidal nature of the variation. When two such strands are combined, one of the following is likely to happen. Now, see, first possibility is that the thin place and thick places of one strand may align perfectly. Okay, with the thin place and thick place. So, thin place and thick place with the other strand. The resulting variations are again sinusoidal, but in double the size. So, thin place is actually aligned with the thin place of other strand, and thick place is aligned with the thick place of other strand. So, that possibility. Now, let us see, this is one strand and next strand is this one. So, this thin place is aligned with this thin place, so but thick place is aligned with this thick place. So, ultimately what will happen? It will be actually magnified. So, double the size. Now, you can see this picture here. So, these are the thick thin places, and these two when we mix we are getting this type of made product. So, here the it is actually magnified, but if we talk about the spectrogram, the nature of spectrograms will be exactly same. So, spectrogram actually measures the this wavelength of the periodic fault. The periodic fault will remain same, and the only the thickness will be doubled, and so for a certain length number of repeat will be same. So, that the chimney is occurring at the exactly at the same position. Okay. Only thing is that the variability of the sliver from the mean size is doubled. However, since mass of the strand is also doubled, the spectrogram shows the periodic variation again. So, this is the periodic variation again, okay, of the same intensity at that point, because intensity will be same, number of because number of repeat will remain same at the same wavelength. And the second possibility is that the thin and thick places of two strand are slightly offset. That means, this is one strand, strand 1, and second strand is like this. It is actually little bit offset. Okay. This type of things are happening. So, then what will happen here? You can see the picture here. Now, this is offset. Now, thin place is actually mixing with the thick place of the other sliver. So, in this way, so finally what we get? We get this type of sliver with relatively even product. That is the target of the Drawframe, and its various mass variation is compensating each other. Okay. Now, here we can see if at all, ideally it should not, there should not be any periodic fault, but if at all it is there, the number of periodic fault, that is repeat, will be less. Okay. Almost it is insignificant. So, there is the periodicity has been eliminated. In such case, the resulting periodic variation become consistently it is lower. So, it will considerably it will be lower, and it is not significant. Under normal practice, what happened? The probability of these things happening is more. So, if we use number of doubling more, so this probability will also increase. So, we will get almost improved sliver. Now, worn out eccentric front roller, front bottom roller in the Drawframe, that let us see what happens. Now, here we have the eccentric bottom roller. front bottom roller here in the draw frame, and it is creating the drafting wave of wavelength equal to the circumference of the front bottom roller, and this, if is front bottom roller diameter is 40 millimeter. So, then it will be drafted 10 times in the roving frame and 25 times in the ring frame. So, effectively the periodic fault which will get in the draw frame, the wavelength will be pi into 4 centimeter, 4 pi centimeter, which will get the periodic fault in the draw frame sliver. The wavelength 4 pi and here in roving frame it will be 4 pi multiplied by 10, 10 times it will be stressed, and the same fault will be stressed here 4 pi multiplied by 10 multiplied by 25. So, the position of the peak or position of the chimney for draw frame sliver will be at 4 pi distance, and for roving it will be 40 pi and it will be then 1000 pi. So, that distance it will be there, that much millimeter distance of the wavelength. So, wavelength at draw frame sliver will be 4 pi, that means 12.56 centimeter, and in wavelength in the roving is 1.26 meter multiplied by this multiplied by 10 multiplied by 25, this will be 31.5 meter. So, that way we can identify the faulty roller, that we will see few calculations. So, eccentrically mounted roller, so 35 millimeter diameter roller giving wavelength of 11 centimeter. So, here that is the at 11 centimeter we will be getting one. So, 35 millimeter means 3.5 multiplied by pi, it is actually close to 11, it is approximately 11. So, here you can see the eccentric roller and where its diameter is 35 millimeter. We get this type of spectrogram. And rollers with pronounced ovality. So, if the oval if there is a little bit eccentricity, then we will get only one peak, but this roller sorry this. So, this is we are getting one peak. Now, if it is oval, considerable ovality, so what we will get, will the roller 35 millimeter roller will be giving the peak at 5.5 centimeter instead of 11 centimeter. Why? So, that means for if it is considerable ovality is there, then for every rotation it will create 2 such peak. Okay. So, this is a 5.5 centimeter approximately, but average roller diameter is 35 millimeter. And due to the can coiling, we get also the periodic fault due to stretching. So, when sliver is laid into the can, it is wound like a coil. So, we have discussed the coiling function. So, at the part of the lower center of the can, the sliver is twisted by the overturning. So, during laying, sliver gets twisted and twist shorten the sliver and increases the cross section temporarily. So, it shorten the length, so that it becomes thicker, and due to that we get a peak. If the faulty coiler head is provided, so for every rotation there will be one fault generated. So, circumference of coiler is produced, that is this peak is at the circumference of the coiler. So, due to the faulty coiler, for every rotation there will be one stretch. So, the fault thus produced is a real periodic variation. So, there in the Drawframe we get this type of fault. So, harmonics means that for a particular there may be condition where many such periodic faults are overlapped. So, several waves are there. So, in that case we get multiple peaks. Now, let us try to do some numerical. Now, here a 40 Ne ring spun yarn is produced from 1 Ne roving. Neglect twist, the drafting roller arrangement in the roving is given in this fashion. So, 40 Ne ring spun yarn is produced from the roving of 1 Ne. This is 1 Ne, and from there we are producing 40 Ne yarn. 40 Ne yarn is produced. So, total draft in the ring frame, total draft will be 40. 40 draft is in the ring. So, the roving is stretched 40 times. Okay. The total draft and break draft at the roving frame is 10 and 1.5. Total draft is 10 and break draft at the back zone it is a 1.2 respectively. The diameters of back roller, middle roller and front roller in the roving frame. So, back roller is B, it is a 30 mm, middle roller is 28 mm and front roller is 30 mm again. Okay. Now, if the middle roller of the roving frame is eccentric, so this middle roller, that is middle bottom roller, because if top roller is eccentric it does not affect. So, that we have discussed. So, if middle roller is eccentric, the position of the peak in meter in the spectrogram of roving and yarn, that you have to calculate. Now, try to see if middle roller is eccentric, the circumference will be pi 2.8 centimeter. So, that will be the periodic fault generated at the middle roller, and then it is drafted at the main draft. What is the main draft? 10 is the total draft and back zone draft is 1.2. This is the main draft, and if we multiply this value with the circumference of middle roller, then we will get the periodic that is wavelength of roving. Now, let us see solution. Draft at the ring frame is 40, front zone draft of roving 10 by 1.2, it is 8.33, and circumference of middle roller is pi 28 by 1000, the middle roller circumference, and the peak location of the roving, the peak is located in the roving is pi, this is the circumference in meter, and multiplied by front zone draft. So, it is becoming 0.73. Now, when we want to measure the yarn, so peak location of yarn, the roving location multiplied by draft in the yarn, this is becoming 29.29. That is the, these are the answers. In this way we can locate, we can get the peak or we can get the wavelength, but in actual industrial use this is not the way we do. We get this value from the spectrogram. After spectrogram analysis we get a peak, and then we try to find the at what is the wavelength. Okay. Wavelength we get, and there after getting wavelength we go backward and then try to find the location. Now, this is one example here. So, 14.7 tex ring spun yarn was tested, and the yarn tex is 14.7 tex and found to have periodic fault of length of periodicity is 57.7 meter. So, wavelength is 57.7 meter. The total draft at the Drawframe, roving frame and ring frame are, Drawframe draft is 6, roving frame 10.5 and ring frame is 25 respectively. The roll size, the size of the roller and draft distribution are given at this stage. So, back roller diameter is 28 mm, back to third roller. So, 4/4 arrangement. So, 1, 2, 3, 4 and this is the calendar roller, 4/4 arrangement. So, third roller, back roller 28 mm, third roller is 25 mm. So, and second roller is 25 mm and front roller 32 mm and calendar roller is 50 mm, and the draft at the back zone draft it is a 1.15 here, and third roller to second roller 1.86 and second to front roller, this is the main zone draft which has not been given, it's we have to calculate, and front roller to calendar roller it is a 1.02. So, this is not given. Now, we have to identify the eccentric roller, faulty or eccentric roller. Now, let us see. periodic wavelength is 57.7 meter, total draft in ring frame is 25 which is given, periodic wavelength of roving which is 57.7 by 25. So, 2.308 and then total draft in roving frame is 10.5 and periodic wavelength of the sliver which is produced is 57.5 divided by 25 into 10.5 and which is equal to 219.8 millimeter. So, whatever the Drawframe is producing the periodic fault in the sliver, that is 219.8 millimeter. So, the diameter of calendar roller is given 50 millimeter. Now, if the calendar roller is faulty, then the wavelength will be circumference of the calendar roller, that let us see, circumference of calendar roller is 157.07 millimeter, which is not matching with the periodic fault in the Drawframe sliver. So, calendar roller chance being the defective is eliminated. Now, next is that the not matching with the wavelength. So, wavelength is more than that. So, it is not the calendar roller. So, next is the draft between the front roller and calendar roller, which is given 1.02, and if we go back, then it is periodic wave length after F. So, when it is delivering after F, that is front roller, the periodic wavelength will be 219.8 divided by the front, the draft here in this zone between front roller and calendar roller. So, it is 215.5 millimeter. Now, let us see the circumference of the front roller, whether it is matching with it or not. So, diameter of front roller is given 32 millimeter and circumference is 100.53 millimeter, and they are not matching with 215 millimeter. So, the front roller also is not the culprit, it is not generating the periodic fault. So, as it is not matching. Now, coming to the next zone between second roller and front roller, which is the main draft, and here draft is not given. Now, what we have to do? We have to calculate this draft, main zone draft. So, total draft by the draft between this. So, total draft of Drawframe is 6 divided by this. So, total draft is 6 and this divided by 1.02 multiplied by 8.6 1.86. So, 1.02 1.86 and this is 1.15 1.02 and this is not given. So, if we have total draft is giving 6. So, if we divide by the other draft, so we will get 75, which is the draft between the second roller and front roller. So, periodic wavelength here in the second, after the second roller is 215.5 divided by 2.75. This is the 215.5. Now, this is equal to 78.5. 78.4 is the wavelength generated at the second roller. Okay. Now, let us see the circumference of the second roller. The periodic wavelength after the second roller is 78.4. Now, diameter of second roller is 25 millimeter. So, 25 millimeter is given. So, if you calculate the circumference, so we get the circumference of second roller is 78.5. So, which is exactly matching with the wavelength generated. So, as the wavelength generated is matching with the second roller, so we have identified the defective roller, which is second bottom roller is the defective, and we can take action, we can replace or repair this second bottom roller. We have to see the second bottom roller. So, matching with the second. So, conclusion, second roll is faulty and there is eccentricity in the second roller. Now, we will stop at this point. So, in the next session we will start another topic, which is variance length curve. Till then, thank you.